Today's presentation, we will present you a couple of open source tools for UEFI work. We will have split the presentation in two between Vincent and me. I will be covering the first half of the presentation, I will be presenting a Linux UEFI validation operating system. And Vincent will be presenting also the CHIPSEC, which is the platform security assessment framework. So moving on to the Linux UEFI validation operating system. Currently, there is no tool to allow you to validate UEFI firmware on Linux from the moment you push the power button and all the way into the point that Linux has boot and is ready to be used. The existing tools tends to focus on a specific area of the execution cycle, for instance, runtime services, or cover only a perspective of try to validate the firmware from a specific perspective, for instance, specification compliance. This leads to insufficient test coverage, and insufficient test coverage leads to causes bugs to make their way onto products that are shipped to the market. And it's already when the products are already in the market that bugs are discovered by the Linux community, by users. And this is bad for everybody. This is bad for the Linux community because the Linux developers get frustrated because instead of spending time developing great features for Linux, they find themselves debugging obscure issues only to find later that they are caused by a firmware bug. This is bad for end users as well, as we saw this morning, because true or not, the systems can be bricked. It may be the fault of the firmware or not, but the perception is that someone has to be blamed, and most of people tend to blame the UEFI firmware. But what can you do to test your firmware properly if the existing tools are so dispersed and focus only on specific areas of the firmware? Well, what we wanted to create was a consolidated product that helps developers and firmware developers and Linux developers to reduce the development time and find more bugs and validate better the firmware. And how do we do this? Well, in the first place, we leverage on the existing validation tools such as FWTS, BIOS bits, and EFI bars, and consolidate them into a single Linux distribution. We also want to contribute to increase the quality of the UEFI firmware by discovering issues earlier, as I will discuss in a minute. We also want to extend the test coverage of firmware, as we feel that there are some areas that are not properly being tested. That is something that I will explain also later. And last but not least, this distribution tool that we are creating is open and free, so everybody can download it, can use it, expand it, and of course, hopefully, contribute to it. Our ultimate goal is to create better UEFI firmware. How? By better validating it, increasing test coverage, and make life easier for everybody. But I also want to take the opportunity to make some precisions about what this new product is not. It's not a new test suite. We are not reinventing the wheel or trying to re-implement whatever people have already developed in other great test suites. Although we do increase the test coverage. For instance, we are paying more attention on boot time services and boot time, in the boot time part of the execution cycle. Also, we are not replacing any of the test suites. Actually, we want to leverage on the existing test suites. We want people to continue contributing to those test suites, and eventually we will take those test suites and incorporate them into our product. We also do not intend to create a certification tool for Linux or a certification tool for UEFI. What we want our product to be used to test how how well behaved is my firmware in Linux? Will my firmware work on Linux? How friendly is it with Linux? Also, as I mentioned earlier, this is not a proprietary tool for Intel. This is an open product, and an open and free product that leverages on open and free test suites. Going more into the details of the product, what we are doing is an operating system. We can also regard it as a Linux distribution. We see here that our Linux distribution is built using Yocto, which allows you to customize your distribution, and allows us also to use the latest and greatest Linux components. We can work on the latest, for instance, in the latest test suite. So every change and every improvement and every new feature that goes into the test suite eventually will land in our product. Another interesting comment that I want to make is that we are basing our product in the latest mainline kernel plus the latest UEFI changes that got merged into the mainline of the Linux kernel at kernel.org. We can appreciate here that we have a number of test suites that runs at different levels of the software stack. There is also a dash line that covers the future features that we will to incorporate. We also want to incorporate test functionality for different bootloaders that are out there. So one may wonder, why create a new distribution if there is already plenty of Linux distribution that could be used for this? Well, one reason that I just mentioned is using the latest and greatest kernel. We know that Linux distributions tend to lag 2 or 3 kernel versions. So if we use the latest kernel, chances are that we will be able to catch integration issues or bugs from the firmware in an earlier stage, and not waiting until the product is already on the market where it create bad press and issues will be harder to resolve. Another reason to utilize a new distribution is that we want to have the capability of testing many bootloaders. We don't want to be tied only to, for instance, Groove or SysLinux. We will in our product we will integrate testing for many bootloaders. And also one may wonder why we want to have many bootloaders. Well, the reason is that different bootloaders are implemented differently and interact differently with the firmware and use different functionality of the firmware. So this clearly increases the test coverage and covers more scenarios on the firmware. Another reason is that having our own distribution allows us to have our own crash handling, because since this distribution is intended to be used in development cycle and for hardware and software, the hardware and the software is not the most stable. So we want to have functionality to handle crashes. So if the kernel crash is not, if the kernel crashes, is not very useful if you cannot know why it crashes or what it is doing. So what we want to do is dump that crash information, and the person who is testing the firmware doesn't have to be a Linux expert to debug it. All he has to do is, all she or he has to do is take that information and send it to our mailing list, and we analyze it and hopefully find the solution for the problem. One last reason to wanting to utilize a Linux distribution is that allows us to test the firmware in scenarios that are closer to real-world scenarios in which the user is putting her system on a given Linux distribution and is using it for different things. And it's different to running a batch of tests for compliance, for specification compliance, for instance. Now, on this slide, what I want to show is how we are increasing the test coverage. As I said, many of the existing test suites tend to focus only on the runtime services. setting variables, getting variables, and I think that we are pretty much covered there. But there are areas in which there are big gaps in the boot coverage. For instance, we have a big gap on in the interaction between the firmware and the Linux kernel at boot time. In the past, whenever a firmware issue was discovered, the Linux community just went ahead and worked around the issue silently without letting anyone know about the issue. And because of that, the issue just got propagated in subsequent releases of the same firmware and in different products. And in our product, what we want to do is warn the user that the issue is still there and it has to be solved. So no longer silently working our own issues. We are giving this tool to be able to find that and hopefully call the attention for the firmware developer to fix the issue. As I just mentioned recently, we are also in increasing the test coverage for the cases in which in the interaction with the bootloader and the firmware, which is as far as I am aware, no one tests that interaction. Future development work. So far, we have released the release candidate number 1 for our project. I will at the end of the presentation there will be some links and references to be able to download the code as well as the binary for the product. But the future development within our scope, as I said, is test several bootloaders, automate the products in which you have you can have a farm of different systems, and each one running a test manager, and these tests can be automated and results can be reported over Ethernet to a central repository. We also want to test incorporate testing for UEFI features such as capsule, network, and secure boot.
This is building on the same theme Mark Doran mentioned this morning about 2014 being the year of testing, quality of implementations, and so to continue that theme. So I'm going to talk to you guys a little bit about something called CHIPSEC, a platform security assessment framework. And so CHIPSEC isn't a single test. It's really an infrastructure, like it's called a framework, to add tests. Predominantly written in Python and has the layered software architecture you see above. There's a version that can run from the UEFI shell, Windows, or Linux, and has some infrastructure elements and capabilities to run different tests. And so I'm going to give you a quick overview of some of the class of tests you can do and some of the design intent behind it. So my parent organization that works on UEFI spec, the EDK2 within Intel, didn't write this infrastructure. Instead, this is from our Security Center of Excellence, the Advanced Threat Research Team. I think that's what they told me to use as their sort of branding. It comes out of their team, but you'll see why we have it here on the docket today. So this infrastructure was actually built for the people in this audience today, BIOS vendors, OEMs, people to do platform validation. And the rationale was this, security threats, researchers keep coming up with new attacks. It's sort of the never-ending cycle. So if a manager says, are you done fixing security issues? Your answer should be no, because there'll probably be an attack next week. So instead of decrying that or putting our head in the sand, we build a dynamic to sort of work within this cycle. So the intent of this is, as new attacks appear, do your mitigation, fix bugs, harden whatever your interface is, and then test whether it has been mitigated. And the class of tests that pass will inform you of your risk. Now, as Jeremiah reminded me before this talk, this doesn't tell you that you're safe, but for a class of emergent attacks, it tells you that you're covered, but it doesn't replace your security development life cycle and your own testing, but it is a way to, as new threats evolve, new tests can be written, assess them against shipping platforms that you may need to patch or future-looking platforms. And again, informing a risk profile. You can never conclusively say you're safe or you're secure, but it helps provide more data with respect to the posture of your machine and some of these emergent threats and even past threats. Maybe you fixed a bug, but in your code maintenance, you reintroduced it, so you can run old tests. And so we talked about threats. So this talk was actually, this talk is modeled on one that Intel gave with MITRE at CanSec West a few weeks ago. So we don't have CanSec West 2014 on here, but the evolution of CHIPSEC and the class of tests that were introduced, you can see were born of an issue that was publicly disclosed, and then the module that was written such that you can test a platform to see if it's exposed to this class of issue. So again, put 2014 on there. There's a lot more. There have already been CanSec West, Syscan, more things are coming. So again, this is sort of an evolutionary process, building a tool like this. And one of the other reasons, I know this is sort of like a lightning talk today, only 10 minutes or so, but really wanted to put this in front of this community because in addition to letting you know there's an open source variant of this, but also to solicit feedback from this community. When you look at it and say, hey, I wish you had, adapted this to take peach fuzz data and do fuzzing of interfaces or some other class of behavior. There's an email address at the end, and I encourage you to talk to me or send mail to that chipsec@intel.com, and please provide that class of feedback. That's part of, again, the reason we're here today is give you a taste of what this is, but also solicit, feedback on what maybe for this class of tool you'd like to see going forward. So, talked about the software diagram, the class of attacks from conferences that have motivated the tests and the specific issues they detect. So what does CHIPSEC look like in action? So this picture essentially, sounds much better, shows the output of the BIOS write protection attack, or protection test, for example. This attack introduced that black hat by MITRE, and so in response to that, for this class of system, an Intel platform with specific registers to affect some of the write protecting, you have now a test that you can run to see if your platform has asserted the write protection. Since the framework is extensible, other silicon vendors could write a similar class of plugin to detect if they have this class of hardware, whether they are similarly protected from this issue. So this is sort of the spewage from one of the tests. Another mode for the test is the direct hardware test from access for manual testing. You can actually use CHIPSEC, peek and poke IO, MSRs, look at CPU ID, decode the SPI bin, see what the descriptors are, dump all the UEFI variables. And so again, since this is Python, there are well-known objects that supply access to this class of various class of interfaces. So you're going to do peeks and pokes and do some forensics on your platform. That's something also possible in CHIPSEC. And then, of course, the forensics. Dump all the information on your SPI ROM, dump your UEFI variables, and then, for example, at CanSec West, there were some attacks described where the appropriate protections weren't applied to UEFI variables. So responsive to that disclosure and that issue, there are tests written such that you can see if this platform is exposed to this issue. So if you have an attack, it's been in the press, there's a tool that can see whether your platform's affected. You put that as part of your manager starts yelling at you, hey, is there any impact for this latest disclosure? You have some positive mechanism to at least start that assessment. Again, it doesn't mean your platform is completely secure, but it provides some observability for some of the issues being brought up by the security researchers. So moving forward, so I'm going to only spend a minute on this and give time for Ricardo to come back and give questions. But in the spirit of testing, that's one of the themes we're trying to unroll today. Invoke the Dijkstra quote, which I think I've been invoking more often than I should have to lately, is testing can show the presence of the errors, not the absence. I think we need to take a broader look as a firmware community on how we do implementation, And some of the sort of thoughts to leave you guys with are some things we've done with Intel. So there's a tool called DDT to do coverage, look for buffer overflows, invalid pointers, something we've adapted for EDK2, but in the spirit of doing something with the community, we're looking to a similar open source version called CLE. It takes the LLVM-IR, so if you can build your code base with CLang and you get the IR, it can do this path analysis, ensure your code has 100% coverage, doesn't have the same class of false positives other static analysis tools may, like Clockwork and Coverity. And then this quote I have from another firmware community where they're talking about embracing similar tools, Framacy, where you decorate your interfaces with sort of specification languages, the expected behaviors, and then have tools to check it. I think testing's great, it's wonderful, we need to do more. CHIPSEC is a way to do extensibility with respect to security testing, but again, testing can't show the absence of errors. I think we need to, as a community, look at how we build code, the actual code artifacts, maybe catch up with the end of the 20th century. There's a lot of great tools out there, and I think we should embrace them as a community. And with that, I'd like to bring Ricardo back to the front, maybe field any questions. I think we have maybe 5 minutes. But if you'd like to play with CHIPSEC, here's the address. It's on GitHub now. I talked to the owning team back in the corner a little bit ago. They didn't have a public roadmap of features they're going to put out there, but there will be a series of additional releases over the next few months. And the team is definitely interested in hearing feedback from this community. You can tell me directly or hit this reflector, chipsec.intel.com. And with that, hey, Ricardo, see if there are any questions responsive to either of our portions of the talk. Good question. So the question was, how long are we going to deal with class 0 systems, legacy BIOS? I think the rule of thumb we had within Intel was after the last Microsoft OS that supports an MBR boot, 10 years from then. So Microsoft, when are you going to stop doing legacy boot? And 10 years from then. So I think it'll be around for a while. Oh, the question was if it's a class 1 and 2 and you have a legacy BIOS or a PCAT BIOS admixture of an EFI BIOS, it depends on the vendor's implementation. What you'll see if it's a PI-based system, you do the PI EFI first and the PCAT compatibility to CSM. That 16-bit code is run later, but there's nothing that prohibits a vendor from having a 16-bit BIOS as their power on self-test mode and then exposing an EFI interface. So there's no architectural prescriptions around that. The only time it becomes, I think this community becomes prescriptive is if you're doing UEFI secure boot, you can't invoke a PCAT legacy option ROM because we don't apply secure boot policy. And so that's a security hole. But beyond that, turn on your hardware. Turing equivalent says it's just code. Run some code. So do what you need to. What do you mean by all? No, so there's some NDA versions of tests. Oh, so the question was, are all the CHIPSEC modules open source? The answer is no, there are some under NDA. There are some that may be responsive to upcoming issues. There may be other criteria that the owning business units around that. So no, the open source is a subset, and to be honest, it's behind on some bug fixes. So no, it's not all out there. Python, and then that HAL layer, when you saw the Linux adaptation, there's native code to grok some services in your execution environment, but everything up is Python, yes. So like if you want to jam on an MSR or something under Windows, you got to go talk Windows native, or do an EFI service call. There's a binding from Python to an EFI call, but everything up top is Python. The expectation is the test writers would just write Python, and the HAL hides the vagaries of your execution environment. So yeah, Python straight up, but no, not everything is open source yet. So the question was, are all the latest Intel chipsets supported? And I feigned ignorance and pointed them to the reflector. I don't know. Yes, is there any room for IHVs to add test cases? Yes, we'd encourage IHVs and the other silicon vendors to add their own test cases. And you can model them on the existing ones that are out there. But since each vendor may have different platform or hardware interfaces and semantics on locks, the intent of this is a framework that everybody can play. So sure. And check them in when you're done, because we need to be a better upstream community, or the Red Hat guy will throw a shoe at me. I don't know. Oh, so the question from our tablet guy was, if you have a tablet that's not necessarily PCAT compatible, this Yocto distribution, will it boot on it? What's the class of platform or expectations of the firmware test suite for class of platforms it'll boot on?
Well, as I will need to point you to our mailing list. Yeah. Yeah, but I believe if we can boot Linux on something, we should be looking into add support for that.
So you've observed, one of the audience has observed, we have 3 sets of tools talked about today: SCTs, firmware test suite, and now CHIPSEC. How do we differentiate? And yeah, I think SCTs to see if the platform has basic conformance, but these are really conformance or positive testing. Firmware test suite can give you some feel about Linux readiness or an alternate OS, and then I think the third, CHIPSEC, is really all about exposure to class of security issues. I don't think CHIPSEC replaces any of them. I think it just complements them. So I think all 3, and run your win check if you're booting Windows, and I think you have to have a test regimen that includes a large class, even more than the 3 we've talked about today. So I don't think it's exclusive or one or the other. It's a good question, though.